will be just a review for all the material that you studied. Welcome back to ME 760 Engineering Analysis 1. Today we'll start with Chapter 9. This is the first lecture. And we'll start with Chapter 9, the vector algebra, where we will just skim through some of the information that you already studied before in previous calculus courses. And the chapter will be easy. This chapter will be easy. And then we will build on the n-dimensional vector spaces and linear vector spaces in chapter number 10. So let's start. So this is chapter 9, vector algebra. And we will start with some definition. So we'll define a scalar, and the scalar is a quantity with only magnitude. So does not have any direction, just magnitude, something like temperature, pressure, and so on, numbers 2, 3, 4, 5. So this is called scalar. And then we'll define the vector, and the vector is a quantity with both magnitude and direction. And some of the vector quantities, something like velocity is a vector, force is a vector, and so on. So how we will do the vector addition and subtraction. So let's assume that we have a vector A, and usually the vectors in the word processing, you will see that the vector will have a bold face, for example. But here, because we cannot write it in bold face, we will either put an arrow in the top of the vector, or you can put a line under the vector. So whatever the reference you want, you can adapt it. So let's assume that you have a vector here, A, then you have another vector here, B, and this is the resultant vector, C, and C equal to A plus B. So if we continue the parallelogram like this, so this will be B also, and this will be A. So this is usually how to add the vectors, and there is certain properties for vector addition. One of them is vector addition is commutative. What does mean? It means that if you add vector A plus vector B, this is the same like adding vector B plus vector A. So if you swap the precedence or the order, it does not affect the resultant. So A plus B is equal to B plus A. So A plus B will give you this vector C, and B plus A will give you, again, same vector like vector C. Another property is called associative. And associative means if you have three vectors now, A plus B plus C, you will have the association A plus B plus C, and it is obvious. So let's assume that you have A, then you have B, then you have C. So you can say that this is the resultant that closes A plus B plus C, and let's say that this is the resultant R. So you can say that it is A plus the summation of B plus C. So this is the summation of C plus B. Or you can say that it is A plus B plus C. So this is A plus B plus C. So this is the associative property. So let's look at the subtraction. And if we have a vector B like this, negative B will be the same magnitude like vector B, but in the opposite direction, so 180 degree. And then let's assume that this is the origin here, and we have a vector here, A. So this will be, this vector is vector A minus B, the addition of vector A plus minus B. So this is A minus B. So let's say that vector A minus vector B is nothing more than vector A plus negative of vector B. So what about vector multiplication? So we'll start the multiplication by a scalar first. So if we have lambda, and lambda is a scalar quantity, and lambda multiplied by vector A might be greater than the vector B, and in this case lambda will be greater than 1. So if you multiply a vector, let's say you have a vector A like this, and you multiply it by a scalar quantity which is greater than 1, so this is the new vector, lambda multiplied by A. And if you multiply it by a scalar quantity which is less than 1, then you will shrink the vector A. Let's assume that this is the vector A, and the vector lambda multiplied by A will be just a smaller version of vector A. And there is again some properties for the vector multiplication by a scalar. So again, if you have the addition of vector A plus vector B, and you multiply it by a scalar quantity, then this will be the distributive property, that you distribute the scalar quantity over the two vectors. So this will be lambda A plus lambda B, and this is called the distributive quantity property, distributive property. Again, if you have two scalars, lambda and beta, for example, multiplied by the vector A, then you can have the association property again. You can have lambda and beta multiplied by the vector A, or you can have beta and then lambda multiplied by the vector A. Lastly, did you have any question? If we have lambda plus beta all is multiplied by the vector A, this will give us lambda multiplied by the vector A plus beta multiplied by the vector A. So this will lead us to the next step, defining what we call the ratio theorem. And usually this is for position vectors. Let's assume that we have a line segment like this from A to B, and we have the origin here. So the position vector for the point A is a vector A, and the position vector for point B is a vector B. And then let's assume that there is a point P that divide the line segment between A and B with the ratio lambda and mu, where lambda and mu are scalars. Then the position vector for the point P will be the vector P here. This is the origin. So O B as a vector is just equal to vector B. OA as a vector is just vector B, and OP as a vector is just vector P. Our goal is to find the point B where it divides the line segment to those two ratios, lambda to A. So the first step, we will see that vector AB, which is AB, is nothing but that vector B minus vector A. Because you will go from, if you want to do the parallelogram or the triangular addition of vectors, you will say, I will start from here to this point, and this is vector A plus vector AB will give me the resultant, which is vector B. So AB is nothing but B minus A. So what about the position vector OP from here to here? So how we will reach to this point? This is the position vector P, and this will be, you go from here to here, which is what? A. Then you add this segment here, but we do not know what's this segment. So let's assume if this is 1 meter, this is 30 centimeters, and this is 70 centimeters. Let's assume. So in order to get this part, we will say that if I divide lambda, which is 30 centimeter, by lambda plus mu, which is 100 centimeter, so this would give me 0.3. So this is the fraction. If I multiply the fraction by the length AB, this will give me what? This segment, yes? Which is 30 centimeter or whatever. So this will be lambda divided by mu plus lambda multiplied by the vector AB. Are you done with this part here? Now, we will replace AB from this equation here by B minus A. So this will give us vector A plus lambda divided by lambda plus mu multiplied by vector B minus vector A. If you just rearrange, this will give you 1 minus lambda divided by lambda plus mu, and this multiplied by the vector A plus lambda divided by lambda plus mu multiplied by the vector B. So this is the position vector P. And this is called, again, the ratio theorem. And this is how to get the position vector P that divides a line segment to a certain ratio, lambda to mu or mu to lambda or whatever. So again, if we replace the ratio, if we replace lambda, and instead of this we put here mu, so, and this is lambda, it does not make any difference. So now let's say we assume that we make it mu instead, so it will be mu over lambda plus mu all multiplied by A plus lambda divided by lambda plus mu all multiplied by P. An example, it is in the book, very nice example. You can just look at the example in the book. I'm not going to go through the whole example, but just to give you the power of this technique. So if you have a triangle, and this triangle is A, the vertices B and C. The origin will be somewhere here. So this is O, the position vector for point A would be just vector A. The position vector for point B will be vector B. The position vector for point C will be just vector C. If we are interested in knowing what is the center point for the triangle. So let's assume that you will get a dividing line from here to here, and this will be point E from the vertex A to here. This would be point F, and then from here to here, this will be point D, and the point of intersection of those three dividing lines will be the point of interest, G. So if you will work out this definition for the position vector, so you will know what's the position vector for this point E, what's the position vector for this point D, what's the position vector for point F. So if you have usually, if you have a triangle like this, and you have this, and this is perpendicular to the base, usually divided to two equal pieces. So the ratio will be 1/2 and 1/2. So just go back to the example in the book, look at it, and you will get the answer that the position vector G is nothing more than 1/3 of the summation of the position vectors A, B, plus C. Any questions? Okay. Let's move on. And look at vector, the basis vectors. So if we are giving different vectors like E1, E2, E3, which are not all in plane, not all in plane. So those three vectors are not in the same plane, so they are in different planes. Let's assume that they are in three-dimensional space now. We're talking about three-dimensional space. So if you are talking about a line, this is what? One-dimensional. If you are talking about a plane, this is two-dimensional. If you are talking about three-dimensional, this will be three-dimensional. Of course, there is n-dimensional spaces, as we will see next lecture. So it is possible that in three-dimensional space we might write any other vector in terms of those three vectors, and this vector that we have here, A, will be just A1 multiplied by the vector E1 plus A2 multiplied by the vector E2 plus A3 multiplied by the vector E3. And in this case, because we will be able to represent any vector as just a scalar component multiplied by the relevant three vectors, we will call those vectors as basis vector. And it will be obvious in a second in three-dimensional Cartesian coordinates what are the three basis vectors. So we will call those basis vectors. And alpha, or A1, A2, and A3 are just the components of vector A with respect to the three basis vectors, and they might be, those three components might be positive or negative or zero. If we want to generalize this in n-dimensional space, we can extend this to, again, C1 E1 plus C2 E2 plus C3 E3 up to Cn En. And in this case, in the n-dimensional space, the basis vectors will be n dimension also. And so we have a couple of properties here that we have to talk about. First, the number of the basis vectors must equal to n. So if we have one-dimensional space, we have one base vector, two-dimensional space, two base vector, three-dimensional space, three base vector, and so on. N-dimensional space, we have n base vectors. And then they should be linearly, they are linearly independent. What do we mean by linearly independent? That this equation, the C1 E1 plus C2 E2 plus C3 E3 and so on up to Cn En should not equal to 0, and C1 C2 up to Cn, all of them should not be equal to 0. Why? Because all of them, if they are equal to 0, this is the trivial solution. 0 multiplied by anything, 0, 0, 0, 0, 0 is the trivial one. But any of them can be equal to 0. But the summation here should not be equal to 0. Why? Because if this summation is equal to 0, what will happen is you can retain the C1 E1 in the left-hand side, then you bring all the other terms in the right-hand side, and then you will represent E1 as a linear combination of the rest of the E vectors. So they will not be linearly independent in this case. So E1 will depend on the rest of the E's. So in order to make them linearly independent, you have to fulfill those two conditions. That this formula should not be equal to 0, and all the coefficients should not be equal to 0. Did you understand? Did you have any question? Okay. So let's talk about basis vectors. In Cartesian coordinates. So in Cartesian coordinates, usually three-dimensional coordinates, we will have three coordinates, x, y, z. Usually in order to represent the orientation of x, y, z, we use the right-hand side rule. So we'll say x goes to y and give us z. So x goes to y and give us z. If you want to put x here, so x goes to y and will give us z here. If we want to go from here, x goes to y and this will be z. So you do not randomly put x, y, and z. You have to have the right-hand side rule. X goes to what? Y. So z will be here. If we reverse, and this will be y, this will be x, I cannot put z as this. Why? Because, and also when you go for the right-hand side, you have to go the short way. What is the shortest path from x to y? Is it this way or this way? You will go this way. So you will have to go from x to y. Did you see it? X to y, z will be where? In the downwards. So you have to retain this into your mind while you are doing this stuff, so that you do not fall into this mistake. Then, if we have a vector, any vector, let's say a vector A like this, you can just decompose this vector to components here. And then we will have three base vectors. One in the x, the other one is in the y, and the third one in the z. And the one in x, usually we denote it as I hat. So this is I, and then this is what? J, and this is what? K. And usually those are the basis vectors in the Cartesian coordinates, and they are equal to unity. So unity, and they have directions in the three coordinate system. So now I can represent A as a component in the x-axis, and this is the component in the x-axis. It's called AX. And this is the component in the y-axis, it's called AY, and this is the component in the z-axis. So those are the three components. So it will be AX in the direction of I, which is in the direction of x-axis, then AY in the direction of J, plus AZ in the direction of K. And those are the three components, and those are the three base vectors. The base vectors, usually we can represent them as I will be 1, 0, 0. What does it mean? It has a unity value in the x direction, because this is what? X, y, and z. The components of any vector x, y, z. So we put them in parentheses like this. If you want to represent a vector, maybe you will say vector A equal to AX, A, Y, and AZ. So the unity vector I is just 1, 0, 0. So it has a unit vector in the direction of x, but it does not have any components in y and z. So what about vector J? Will be what? 0, 1, 0. And what about vector K? Will be 0, 0, 1. Did you understand? Okay, so what about the amplitude or magnitude of vector A? How to get the magnitude of vector A? It's nothing more than the Pythagorean theorem. Yes? So AY, this is AX, again, this is AX again. Yes? And this is a 90-degree triangle, this one. So this is equal to AY square plus AX square under the square root. Yes? Okay, and there is another triangle, which is the vertical triangle here, a 90-degree. So this is equal to this square plus this square. Yes? But this one is what? Square root of AX square plus AY square. So in order to get this, it will be AZ square plus this square, and this square is what? AX square plus AY square under the square root. Yes? Because this is this plus this under the square under the square root. So in this case, we will have vector A. The amplitude of vector A we represent it as like this. This is the amplitude of vector A, and it is nothing more than AX squared plus AY squared plus AZ squared, all under the square root. So this is the amplitude of any vector in three-dimensional space. What about the unit vector of a vector? If you want to get a unit vector of a vector, so the unit vector is nothing more than A hat. So if the vector is A and there is an arrow in top of the vector, the unit vector is A hat, which is just a unity vector. It has an amplitude or magnitude of 1, and it is in the same direction of the vector. So if the vector is pointing like this, and I want to get the unit vector, what should I do? I will simply divide the vector A divided by the amplitude of the same vector. Do you remember just a couple of minutes at the early of the class, we said that if we multiply lambda by A, it might be greater than A, or it might be less than A. For this case, lambda should be what? Greater than unity. And for this case, lambda should be what? Less than unity. So you can do what? You can do manipulation for vectors. You can extend the vector by elongating the vector if you multiply by greater than 1, or shrink the vector if you multiply by a vector less than 1. So if you divide the vector by its magnitude, what did you do for the vector? You make it unity. Normalization. You normalize the vector. You make it unity. And this is A over the amplitude of A. So the properties of in three-dimensional space of vector addition, we have vector A plus vector V, then this will be just AX multiplied plus BX in the I direction plus AY plus BY in the J direction plus AZ plus BZ in the K direction. This is very simple, because if you have two vectors, let's assume that you have another vector like this, then you have the components, yes, and then this vector will have AX in this direction, yes, and the vector B will be BX in this direction. So you have two vectors in the X direction. One is called AX and the other one is called BX. How we will add them? Just mathematical addition. So it will be AX plus BX. So AX plus BX in I direction. And then you will have another AY plus BY in Y direction and AZ plus BZ in the Z direction. So this is just the simple addition rule. So what about vector multiplication? What about vector multiplication? So there is two cases for vector multiplication. The first one is just multiplying a vector by a scalar, as we just stated or before. And now there is a vector multiplication. So we just, at the very early beginning of the class, we just show the scalar multiplication of vectors, or vector multiplication by a scalar. Vector multiplication by a scalar. So now, what about the vector multiplication by a vector? We have two things. First one is called scalar product. For vectors. And sometimes you will find that people define it like dot product, and they give it A dot B. They name it A dot B. So how we will multiply vectors using this scalar multiplication. So it's nothing more than, if you have a vector A, and then you have another vector B, and in between them there is an angle theta. To do the vector multiplication, A dot B is nothing more than the amplitude of vector A multiplied by the amplitude of vector B multiplied by the cosine of the angle theta, where theta should be anywhere between 0 and 180 degrees. 0 to 180 degrees. And in this case, A dot B is a scalar quantity. So A dot B is a scalar quantity. So what's the geometrical representation of this scalar multiplication? So it's the amplitude of A multiplied by the amplitude of B multiplied by the cosine. So if we have the projection of A over B, so what's this? So this is A sine theta, and this is a cosine theta. Yes? So when you do the scalar multiplication, you just do the projection of A over the vector B and then multiply by vector B. So this is just the vector representation. So if we have the properties of the vector, if we have vector A dotted with vector B, and the dot product is equal to 0. So what does it mean? If the vector A dotted with vector B are equal to 0, they are, no, theta is not 0. If theta is 0, cosine 0 is 1. So they are perpendicular vector. So for any perpendicular vector, we call it orthogonal or perpendicular. Orthogonal or perpendicular. The vector the other property is A dot B is equal to B dot A, which is commutative. They are commutative. If we have A dotted with vector C plus vector B, this will be A dot vector C plus A dot vector B, and this is distributive. Again, if we dot a vector A dotted with the unit vector in the x-axis, what does it mean? If we have a vector here and we have the dot product, this is in the three-dimensional space, and we dotted this vector with the I component. So this is the projection of vector A on the x-axis, and it is just a cosine theta. The axis, the three cosine angles, or three angles for the Cartesian coordinates, we call them alpha, beta, and gamma. Alpha between the vector and x-axis, beta between the vector and y-axis, and gamma. So this angle is called what? Alpha, and this is beta, and this is gamma. So this will give us the amplitude of A cosine alpha. And from there, we can get cosine alpha is nothing more than this one is nothing more than AX. Yes? So A dot I is nothing more than AX. So this will be the x component of the vector divided by the amplitude of the vector. Yes? Because if you come here, this is the amplitude of the vector in the z-axis, and this is called what? AZ. So if you get this triangle, this is the vector A, and this is what? AZ, and this is 90 degree. And this angle is what? Gamma. So if you divide the amplitude of A, if you divide AZ by the amplitude of A, this will give you what? Cosine what? Cosine gamma. Did you understand? Same. Cosine alpha is AX over amplitude of A. Cosine beta is amplitude AY over the amplitude of Y. So we'll do an example here. Did you have any question? So again, if we have a vector A and a vector B, and there is an angle theta, then this is what I just drew before. So this is the vector A. It has an angle here with the x-axis, y-axis, z-axis, and this is alpha, this is beta, and this is gamma. So A dot B is nothing more than AX BX plus AZ BZ plus AY BY. Somebody will say, how did you obtain this? So the scalar multiplication is this, but also you can make it like AXI plus AYJ plus AZK dotted with BXI plus BYJ plus BK BZK. Then you will multiply each term individually. So this would be AX multiplied by AY, and then you will have I dotted with I plus, yes, X multiplied by BY, I dotted with J, and so on. Yes? So I dot I, the vector you multiply it by itself. What's the angle between the vector and itself? 0. Cosine 0 is 1. I and I, 1 multiplied by 1. Cosine 0 is 1, so it's 1. So you will have AX, AY. Yes? If we come to this one, what's the vector multiplication of two perpendicular vector? 90 degree. So you will eliminate all I, J, J, I, K, K, I, K, J, J, K. And the remaining will be I, J, J, and K, K. So I will produce AX, BX. AX, sorry, this is BX. AX, BX. Okay? So you will have AX, BX, AY, BY, AZ, BZ. And this is this one here. So the vector multiplication can be the amplitude of the first vector multiplied by the amplitude of the second vector multiplied by cosine of the angle between them, or it might be the multiplication of the relevant components. AX, BX plus AY, BY plus AZ, BZ. Did you understand? Okay, so we have it like this, and this is also equivalent to A, the amplitude of vector A multiplied by the amplitude of vector B multiplied by cosine the angle between the two vectors. For right now, everything is okay. So let's make cosine theta in one side, and I will say that cosine theta is nothing more than AX BX plus AZ BZ plus AY BY. All of them are divided by the amplitude of vector A divided by the amplitude of vector B. Is it okay? Now, you will divide the first term, AX, BX, by this first. But then you will have AZ, BZ, again by amplitude of A and amplitude of B. Then you have AY, BY, divided by the relevant amplitudes. So what's this? AX over the amplitude of X. Huh? AX, let's make it simple here. AZ divided by A. Cosine gamma. So if it is AX divided by A, it's cosine what? So this is cosine alpha, but because it came from the vector A, I will call it alpha for the vector A. Yes? And this is what? Cosine alpha for the vector B. And this one I will call it what? Cosine gamma for vector A multiplied by cosine gamma for vector B plus cosine beta for vector A multiplied by cosine beta for vector B. And this is a very useful relation that correlate the angle between the two vectors theta with respect to the angles of the coordinate system. So this is not in the book, so you might keep it and you know how to derive it, and this is just a simple example. So in nuclear engineering, reactor physics, for example, if you want to study at the very early beginning how the neutron interact with matter, for example, with atomic nuclei, you will have the laws of mechanics, and you have to decompose the neutron vector momentum in the three components, and in this case you might need this formula or so. So we will stop here and we will continue next time.